Okay, so now it's time for the second part, and this one is going to be maybe a little bit more fun. It's going to go off script more than the first part. So we'll cover a lot more advanced things and really cool template features as well. So the first big part of what we'll look at is going to be variatic templates. And yeah, perhaps a standard quote is going to illustrate what exactly this is. So the template parameter pack is a template parameter that accepts 0 or more template arguments. So we're by no means limited to just accepting, I don't know, a single int or a single float or something like that. We can accept an arbitrary amount of these, right? And we can accept distinct types as well. We can accept, I don't know, int, float, double, etc. All of these in just a single parameter. Yeah, and a function parameter pack is a function parameter that accepts 0 or more function arguments. So here you can see an example of a template parameter pack, and this, for instance, would be a function parameter pack. And these can be very useful because they allow us to create containers that can store, you know, an arbitrary amount of distinct types. So for instance, if we had something like a tuple type, which you'll find in most programming languages, I should probably reset the counter as well. So if you have something like a tuple type that can store an int and then a float and then a double, etc., a lot of programming languages support this kind of feature. And we could implement that using C++. So for instance, if you look up the like the implementation of tuple in Rust, you will find that it's like the same thing copied and pasted 30 times. But standard tuple is defined without copy and paste. You know, it can be entirely self-hosted and defined elegantly in C++ using these variatic templates. Now, okay, this tuple right here, it doesn't actually store anything because, as it turns out, it's kind of complicated to store like a pack as members. But yeah. This one is just empty, but it still illustrates the idea. You know, we can have a tuple that stores absolutely nothing. We can have a tuple that stores an int and a float. All of this is possible. And yeah, we can have variatic functions as well, which allow us to, you know, kind of perform the same operation, but on an arbitrary amount of function parameters. Okay, so there are some questions. Notice how the ... has weird alternating fixity. I'm not actually sure what you mean by alternating fixity. Yeah, do you mean like syntactically or so, that in this case it kind of belongs to the type name, and in another situation it belongs to the args? Yeah, I don't know. That's a question for another day, how to actually style this. I mean, that's a style guide thing at the end of the day. How would the full min function be implemented? Are the arguments passed in as an array? Oh yeah, here's where it gets fun. Because what I wanted to do with you together is to basically implement this min function from scratch. Because I think the min function, you know, a variatic min function is an excellent exploration of like variatic templates and how they work. Okay, so we have the following problem. We basically want to write a min function that doesn't just work for 2, but that works for, you know, an arbitrary amount of these, right? So this is going to be the code that, you know, one day hopefully is going to work. Right now it doesn't, because, you know, this doesn't really do what it's supposed to do. We have unused parameters. This doesn't return anything. We're in deep trouble. So we need to implement this. Is template int... Yeah, okay, so to go back to the previous slide to answer the question, is template type name t and then foo of this unpacking twice? No. That is actually a... Yeah, this it's just, I can't let this be. This is too funny of a thing. So type name like args, right? So let's say you have some variatic function like this that accepts args. Right, this is possible in C++. But what this actually means is that you have some args, right? So these are the variatic arguments from this parameter, in the parameter pack, followed by an ellipses parameter, right? So this is actually C-style variatics, so the same stuff that you would find in printf, right? But if you omit the name, if you omit the comma, if you omit everything, then yeah, you just end up with 6 dots, and this looks insane. I don't know. Surprise your coworkers with this kind of thing. It's funny, but yeah, let's get rid of this trash. Okay, so we have a min function that we want to implement. Now, how can we do this? One very basic tool that you have with parameter packs is recursion. So this is going to look very similar to certain like functional programming languages. So with recursion, it's kind of useful to split things up, right? So let's say we have a head parameter and then a tail parameter, right? So basically we kind of grab the first element, or well, the first type in the pack. So for instance, our min function, then, you know, we want the 7 to basically become the head, and then 3, 4, and 10 is going to become the tail. So this is the recursive implementation. So then we have the tail parameter. And if we then wanted to do something, so let's, so now to implement the min, we basically need to compute the min of the head and the minimum of everything in the tail that remains. There is, however, a little bit of a problem, because we have not been clever enough about this. The issue is that when this gets to the very end, so when this gets to the 10, 10 is going to be the head, and as we've previously read, the tail, you know, it can have a length of 0. However, we can't actually call this with an empty pack, right? So here it says no matching function call for call to min, and it says that the candidate is ignored. What does it say? Well, let's enlarge this. So yeah, candidate expects at least 1 argument and 0 provided, right? So we've not been clever enough about this. We need to do something differently. Now, what you would do in C++ 11, oftentimes in C++ 14, is to kind of define a base case. So, for instance, you can define a non-templated, or one that only accepts a single parameter. So this is going to be then head min of just the head, right? And this is going to return the head itself. All right, so this is then going to be a base case. However, this is still not smart enough, because now if we're calling this with only a single parameter, right, then we run into the issue that if the tail is empty, both of these functions here, right, both of these functions are equally viable. So overload resolution gets confused. Wait, what? That actually worked? Okay, wait. That's interesting. Okay, so I guess the issue was something else. Yeah, I guess that does work then. Interesting. Yeah, okay, so I suppose this one actually does win an overload resolution because it doesn't have a, because it's not variatic, because it doesn't have a template parameter pack. So that actually does make sense that this one would win an overload resolution. And so this is how we can define it. Now using modern C++ tools, this can get a lot better looking, or at least it can get, well, we can still define this recursively, but we can actually do this in a single function, right? So since C++ 17, there is the const expr if statement. And what this can do basically is make a decision at compile time. So if we do if const expr, well, how does this, okay, so there's the question, how does this actually work? Well, I'm not I'm not sure what you're exactly referring to, but perhaps I haven't explained this this explicitly enough. So basically what happens for a min function, right? So what happens for 7, 3, 4, and 10 is that we're passing this into min, right? So the head is going to be 7, 3, 4, and 10 are going to be the tail, right? And then it calls itself recursively again. So the next time 3 is going to be the head, and the tail is going to be 4 and 10. And then the final time, 4 is going to be the head, 10 is going to be the tail. Yeah, and then at the very, very end, right, there's only going to be a 10. And so it reaches the base case, and it returns the head itself. I've also just realized that this is not a min function. It doesn't actually do anything useful, yeah. Yeah, we need to kind of return the actual minimum. So like if the head is lower than the minimum of the tail, then we want to return the head, and otherwise the minimum of the tail. Now, ideally, to not have multiple evaluations, you would also like put this into a separate parameter right here. So let's say head tail min, and then we kind of return the and then return the minimum of this and that. But anyhow, the point is that in the base case, right, this is going to just be 10, and this function right here is going to be called, right? So this one is just going to be, yeah, so for 10, it just returns 10. And then for 4 and 10, this is then going to obtain the minimum of the tail, which is 10, and it's going to also use 4 right here, and it's going to pick the lower of the two values, which is 4, right? And then basically we kind of like exit this, we go one up the call stack again, and we then have the minimum of the tail, which is 4 and 10, and 3, and we pick the lower value, which is 3. And then in the final step, when we unwind everything, the minimum of the tail is 3, well, it's the minimum of 3, 4, and 10, right? So that's 3, and we pick the lower value of 7 and 3, right? And so ultimately, here you can see that, hold on, why is x 0? I've clearly messed something up. Yeah, now wait until you need perfect forwarding. I would prefer not to get into perfect forwarding just now. Yeah, actually, I'm kind of asking myself why exactly is this 0, because there is no 0 in here. So I'm a little confused. Where does that 0 come from? Okay, this is bizarre. I've wanted to do this stuff in a more improvisational manner. Wait, so what is the min of 7? This makes no sense. What? Oh wait, no, this is just padding. No, indeed, this is 3. Yeah, I guess it's because it's extern or something. I'm not sure. Yeah, this is a little weird. I guess because it's not const expr, so that's why the initialization is taking place at runtime, and why it's initially 0. That had me confused for a second. Now we can see in the assembly output that yes, indeed, this is all 3. Yeah, isn't this dynamic initialization? That's exactly right. We have forgotten to put a const expr on it and so on. Like, this is happening at runtime. But anyhow, this is one option. And as I've said, we can make this a little bit prettier. So in C++ 17, you have const expr if statements, which are very helpful with variatic templates. So for instance, what you can do is you can test whether the size of the tail, so as in the actual number of parameters inside of that, is equal to, let's say, 0. Right, in that case, you just return head. And otherwise, we do everything that we've done before. So using this const expr if statement, we can make this function a whole lot more pretty. Well, okay, it's not prettier, but at least we only have one of these now. So that's cool. And everything still works as intended, but we don't need overload resolution. This is, in a certain sense, it's much easier. It's much simpler now. So yeah, so that's a cool thing. Then another feature in C++ 17 is fold expressions. And these, like, the idea of fold expressions is that if you have a pack of something, then you can combine each element of the pack using some kind of operation, right? So a very simple example for fold expressions. Let's say we have some, well, int sum, or let's say autosum, let's be a little bit more idiomatic. So we have an autosum of some types, and we want to return basically all of these, summed up together, right? So then you can use fold expressions, which are always included in parentheses. So args plus the remainder of this, and that's how it works. So what the compiler basically does in this place is, if we, let's say, had a sum of ints, of some, value, like for an int, and then another int, and then another int, then it just turns this into like the first argument plus the second argument plus the third argument. So once again, I mean, this is kind of a copy-paste mechanism as well, but we can let the compiler do this for us. It just turns into a bunch of plus operators, right? So for instance, if we call this with 2, then it would just be, like the first one plus the second one, and so on. And this is a very useful feature because it allows us to do absolutely crazy stuff. Not only can we do this with, okay, let's maybe demonstrate how this works. So for instance, let's say we have int y equals sum of 1, 2, 3, and in the output, this, once we make it const expr, should basically be equal to 6. Yes, exactly. Right, so that's how it works. It just kind of takes the 1 and then puts a plus operator between that, and then the 2, and then another plus operator, and then the 3. And in order to be safe for empty packs, we also kind of need to define a base case, right? So that can go on the right-hand side, it can go on the left-hand side, etc. And so that's fold expressions. When are you supposed to put an ellipsis in and when not? For parameter packs, you never use ellipses arguments, right? Like the syntax with the 3 dots, that's just part of the like parameter pack syntax. But you don't really use C variatics in C++. Now, okay, sure, if you want to kind of recreate printf in C++, then I guess you have to do that. But it's something that you would want to avoid, because like C-style variatics, they just don't work very well in C++. They have absolutely no type safety, and like if I had $1 every time I saw somebody messing up the usage of printf, then I would have, I don't know, $50 probably. So yeah. Well, a parameter pack, as I've explained in the definitions previously, is basically a parameter that can hold 0 or more types than that, so just an arbitrary amount of these. Does this break GCC's range initialization and range switch cases? I'm not sure. I honestly don't know too much about all the GNU compiler extensions, if that's some kind of GCC specific feature. So I'm not 100% sure. But yeah, a really cool thing that you can do with fold expressions is that you can kind of create proxy types and turn things into operators that were never operators before. So let's do that real quick. So what we'll do is we'll create some kind of, wrapper. So this is super simple stuff. It's just kind of a wrapper for some value. And we define an operation on this. So let's say we overload the plus operator. So that'll be wrapper of t operator plus wrapper of t, something else, other. And now we make this the min operation, right? So instead of defining this to work the way that a plus operator normally works, we make it work like a min function, right? So for instance, now what you could do is you could check whether like the value is lower than the other value, and then pick the value and otherwise other dot value, right? So this is just kind of how the min function would normally work. And yeah, I suppose we still need to be explicit about this one and put it into braces. And now comes the magic. With the help of this kind of, you know, wrapper type, proxy type, however you call it, you can simplify this min function even more. You will be amazed to see how this is going to work out. So a min function can now just be defined like this, right? So no longer head and tail is just going to be doing everything at once. So let's say for args. And now we return wrapper of t for every single args. Okay, something doesn't quite work. What is going wrong? Cannot convert wrapper of int to int. Oh yeah. Well, we still need to get out the value at the end of the day. But yes, look at how short this has now become. So essentially, oh, hold on, stop annoying me. So yeah, and now x is still 3, right? So everything still works as intended. This is still basically a single 3, right? However, we have kind of hijacked fold expressions by using some kind of proxy type, some kind of wrapper type. And yeah. Wait, so there's a question from chat. So args lower than something and then doesn't work. So basically the question is whether we can use the conditional operator in combination with fold expressions. And I'm 90% sure we can't. I seriously hope I'm not wrong. But I'm 90% sure that's not possible. No, I don't even know how you would define this. It has to be a binary operator, right? Okay, so I've looked it up. No, it's not possible. It needs to be a binary operator. It can't be anything else, right? And now maybe if you don't understand this this example 100% yet, so basically what happens here is that every single one of these arguments, right? So every one of these int arguments is going to be wrapped in this wrapper, right? And then each one of these is going to be combined using this plus operator. And so the result of this, I suppose, is that yeah, we use the plus operator between them, which is really a min operator, I guess. We've made it behave like min. And at the end of the day, we just extract the value out of this. So really, this kind of turns into you know, like wrapper of int 7 plus wrapper of int like 3 and etc. etc. Right? So that's basically what it turns into. That's how fold expressions work. Yeah, Jakub Gamer is asking, how long will this const still last? Well, I mean, this presentation is going to end probably in like half an hour. However, there is a CPPCon every week, and let's see how long we can kind of keep that up. So yeah, and now that you understand variatic templates, what kind of cool stuff you can do with them, I would just want to kind of look at the toolbox, what things you can do in general, just kind of list all of them, right? So one very common operation with packs is that you would want to put them into some kind of container, right? And this is happening using pack expansions. Now, I haven't actually shown you pack expansions yet, and it's probably best if I do that, right? So, for instance, if you have this, I don't know, I'm just gonna grab this guy here, right? Let's say you want to put this into an array, right? Like, okay, this is not gonna do anything useful. This is just for demonstration purposes. So if we wanted to have an array, we could initialize this to basically every single thing in the pack. And so what this will turn into is just kind of int array, and then 1, 2, 3 when we pass in a pack of 1, 2, and 3. Right. So for instance, you can, I guess, well, it doesn't return anything, so I can't really instantiate it right now. But that's the basic idea. So pack expansions, they've been around since C++11, and for instance, they allow you to put stuff into some kind of initializer list. Also, you can call things recursively by expanding packs. So we've actually done that in the min function as well, right? So this is about the most basic thing that you can kind of do with parameter packs. And the next thing is this pack reduction. So this is what I've talked about. You have many things in a pack, but you want to turn it into just one thing, right? Maybe you want to add all of them up, and maybe you want to get the minimum of all of these, right? That sort of stuff. And you do that using fold expressions. So yeah, you have fold expressions. Then I've also kind of showed you the, the pseudo-fold expressions. I'll probably dive into that for 1 second as well. But yeah, you have fold expressions with proxy types. So this is what we've done in order to kind of simplify our min function, well, at least make it more concise, right? So basically the trick of, creating a new wrapper type or proxy type and then hijacking the usual functionality of fold expressions. I'll get to this one in just a second. And the min has become shorter, but some of the code has been displaced into the wrapper. Well, yeah, sure, that is absolutely the case, but at least we don't have a recursive function. So we don't need to worry about stuff like the stack depth, etc. We don't need to put as much faith into compiler optimization. We have a more concise definition. So like the code is just, like the relevant pieces are more simple and they're spread out over more code, I guess, instead of just being one contrived thing. I mean, it's still a stylistic preference to some extent, right? So yeah, it does have advantages. It does have disadvantages to kind of pull this trick off. If you're using C++14, I guess you don't have a choice anyway, so whatever. What about a template of variable non-types like int args? Yeah, you can totally do that as well. Like you can have a template, template int, I don't know, n, then void bar. So this is totally okay. Now the question is, how useful is this? Because, for instance, in a lot of cases you would have to specify this explicitly. So for instance, now if we wanted to in z equals bar of like 1, 2, 3, etc. Sure, we can do that. That's perfectly fine. But now we have to specify each one of these explicitly. I would generally say that non-type packs are not useful that often. It's probably useful if you have a container that has a pack of these and you want to deduce it, but yeah, it's maybe not generally that useful, but it's possible. And in fact, this can be auto, in which case it's going to accept anything, not just int. I guess you should make a wrapper that takes a lambda. I'm not exactly sure how that's how that would benefit it. Yeah, I'm not 100% sure what that would exactly accomplish. So yeah, anyhow, next really fun feature, so pseudo-fold expressions. So the thing is that fold expressions, there's a C++17 feature, there's a high chance that you don't use C++17, right? You might be still stuck on C++11 and C++14. Now, good news, you can actually reduce many things to one, even before fold expressions were a thing, right? So let's say we wanted to re-implement our sum right here, but using only C++11 features. So here's where it gets a little bit funky. I can feel my brain cells slowly decomposing and necrotizing. Well, that's C++ templates for you. I don't know. I guess you love it or hate it. Maybe both at the same time. So, yeah, so this is going to be an old school implementation of a variadic sum, but without any kind of fold expressions and without any kind of recursion. So what we can do is we can kind of hijack pack expansion. So we'll just define something that's discarded. I don't know, just use an underscore as an identifier here, right? And args. Right, this on its own is not very useful yet. However, now comes in the magic, I guess. So let's say we have a sum of, initialized to 0, and we return the sum at the end. This is still not particularly useful because, I mean, what it does is it just returns 0, regardless of what we do. It's still not useful, but it will be in a second. Okay, so here's where it gets really funny. Wait, hold on. Why exactly is this failing to compile? I mean, it shouldn't. I don't know. Unused variable, whatever. So what we could do is, since we can put any arbitrary expression in a pack expansion, we could actually use this opportunity to add something onto the sum. Right? So for instance, we can say sum plus equals args, right? And this is going to happen for every single one of these. And now, as you can see, we have successfully turned this pack expansion into, well, essentially something that returns the sum of this. But you can see that it's not really as powerful. First of all, you need more lines of code to accomplish the same. It's also more annoying, like, and the syntax for it is totally bizarre. Also, the problem is that you don't really get the same like type deduction stuff. So this is going to be messy. Like, it has to be an int, or it has to be some other type that you kind of know in advance. However, you could get one from the pack. That's also possible. But yeah, the overall capabilities of this are less. But it's still nice to have something non-recursive to maybe sum up a pack of something or combine it in another way, even before C++ 17. It's just some, it's just an idiom that is worth mentioning because I think it is actually somewhat cool. Yeah, the problem is, I mean, this is kind of unused right now. I guess we could just put faith into the compiler figuring that out. And so, okay, so why is this exactly failing anyways? In instantiation required from here, unused variable. Wait, so why is that a compiler error? Oh, it's just a warning, okay, but it gets highlighted as red. I was confused about this, but it still compiles, okay. Can you construct a temporary array? Well, the problem is that in C++, that's not, totally, it's not possible syntactically without some kind of variable template. I mean a type alias template. So for instance, we could define this very useful array type equals T array. So what this does, right, is this is an alias template that just kind of turns this into the array, well, into an array of unspecified size of this, right? And now, lo and behold, we actually can do this. Okay, it doesn't get deduced, but we can do it for, let's say, int. And yeah, and now we could also cast this to void in order to discard the whole thing. So the compiler isn't gonna complain about this being unused or whatever anymore, etc. But yeah, so this is the general idea of imitating fold expressions before C++ 17. It's possible. Whether it's all that useful is arguable. It's definitely not pretty, right? So then, pack filtering, I don't really have the time to go into all the, details with this. But using like fold expressions and proxy types and stuff, it's also possible to kind of just, filter out a portion of a pack. So let's say, pick every parameter that is an integral type or any one that is a floating point type. And yeah, and then finally pack creation, that's also worth mentioning. So there are situations where you don't actually have a pack, and you want to turn something that isn't one into a pack. So this is happening using the standard make index sequence type from the standard library. Or actually, it's a function actually. So there's a question in chat. Does the expansion work everywhere or just in initializers? No, like the expansion has to happen inside of a function call, or it has to happen inside of the initializer list of something, right? So we're kind of limited. We can't just do it anywhere. So that's kind of unfortunate. Yeah, but anyhow, so it is worth mentioning that if you don't have a pack yet, and you want to turn something that isn't a pack into a pack, so let's say, concrete function time, right? No templates right here. So let's say you have some kind of array, right? Of let's say 1, 2, 3, and you want to use the sum function with this, right? Well, what you could do is basically sum, array 0, array 1, array 2, right? But now you're making yourself the tool. Now you're copying and pasting, right? What are you doing? That's not okay. We can accomplish the same effect using something from the standard library, for which we are going to have to include type traits. And so let me type this out because it needs a little bit of focus. So let's just make this auto, and then the sum of standard index sequence of I, and we also need another, well actually this comes from tuple. That's the thing, it comes from tuple. And yeah, let's say we still want to deduce the size of our array. So we have a reference to an int array, and we return this right here. But before I dive into all the details with this, I would first like to answer the questions from chat. So, can you do a standard vector of int and sum and then plus equals this stuff? Yeah, I mean, you can totally do this. Yeah, you can totally put this into the initializer list of a vector. That's totally fine, right? You can put it into like any initializer or any function call. So there is no limitation when it comes to that. Whether you should use a vector for this is another question. In this case, probably not. I mean, you just kind of want to get rid of it. So that's perhaps not a great idea. But yeah, I mean, in principle, yeah, it would work with vector as well. There's one missing step to this. One missing step. Namely, we have to use this magical, almost magical function from the standard library. The standard make index sequence. And in this case, for an array of size 3. And this is going to make the index sequence. And now you can see that if we were to return the sum, so now if we were to return the sum, you can see that the main function correctly does move 6 into EAX, which tells us that yes, indeed, the sum of this is 6. Now the basic idea is that we use this make index sequence function to just kind of create this index sequence. And the index sequence is basically a type that looks somewhat like this. So it just has a bunch of these parameters. It's actually a pack index sequence, and it doesn't contain anything, right? So that's kind of how an index sequence looks, or how a standard index sequence in general looks. So basically what we can do is we can tell the standard library, hey, make an index sequence for us with length 3. And then when we pass it into sum, we can deduce these indices that we've put into it. So these are going to be, 0, 1, and 2. This is what standard make index sequence does, is it basically creates an index sequences with 0, 1, and 2 and stuff like that. And we can use this pack in a fold expression, right? So now for every single I, so for I equals 0, I equals 1, I equals 2, etc., we just access the array at this index and we add all of them together using a fold expression, right? So this is kind of useful. There are situations where you don't have a pack and you want to have a pack, right? This is common, for instance, when you're interacting with standard tuple or some other kind of variatic container. Then oftentimes you have a container, but you don't have a pack. So that's this is just a way of getting a pack, so to speak. And yeah, that pretty much covers all of the cases. So to summarize, if we want to have a pack stored in a container, just expand it, put it into the initializer list, pretty straightforward. If we want to reduce all of them together, we want to get the minimum of all of them. If we want to add them all together, yeah, we can do that by reducing the pack. Yeah, we can do the same with like filtering the pack, although I won't go into detail with that one. And if we want to create a pack out of thin air, that's also possible using the standard library, although you could do this yourself recursively, it would just be far less efficient. Because the standard library has intrinsics, it has compiler magic that makes this extra fast. So you don't have to use recursion. Yeah, const expr if statements, I've already touched on these. Perhaps it's important to emphasize that they're more than just an if statement that gets run at compile time, right? So that is obviously the first point. It's guaranteed to be evaluated at compile time. And we've used this in the, in the min function that we've written, right? So we've kind of checked, is the size of this pack equal to 0 or is it not? But the other important aspect is that it just completely prevents instantiation of the block if it's false. And yeah, with this you can make complex decisions that are all guaranteed to be evaluated at compile time, even decisions that like influence the return type and all sorts of stuff. You can sometimes save on like overloads, as we've done with the min function. Like if you recall, we had two min functions, one for the base case of just a single element and one for the case where we have more than one, right? And we've turned that into just a single function. So if const expr, generally very useful feature. Here's another example of where if const expr can kind of come in handy. This is kind of similar to why it's useful for a min function. So let's say you want to have some kind of generic stringify function, right? So what it's supposed to do is it takes a float and it turns it into like a string that represents the float. Or it takes an int, it's supposed to turn it into, well, a string that represents this int. So what you could do is, for instance, you could check whether the type is arithmetic. And in that case, you return standard toString. And alternatively, as kind of a fallback solution, if there's nothing that you can come up with, if it's not an arithmetic type, meaning that standard toString won't be defined for it, then yeah, you could basically use string streams as a fallback and try to stringify it like this. The thing is, this is actually not going to work for a type that, I can't actually demonstrate this very nicely. Because every arithmetic type is also stringifiable using the string stream. But the important thing is that if this was a regular if statement, right? So if this was just if, and we passed in some kind of custom type, some kind of user-defined type. Well, hold on, I can absolutely demonstrate this. So first of all, we need string in order to make this work. I think type traits is also kind of leaked through the header. Yeah, totally is. So let's say we had some struct s, just for demonstration purposes, and yeah, we should give it this operator, so at least something is going to work. At least the fallback is going to work. And yeah, this is just not gonna do anything, right? Out, and it's just gonna return it, right? It's not gonna print anything. This is just kind of a dummy here, right? So now if we wanted to, let's say, stringify s, this is going to work. Because if we stringify a new instance of s, it's going to see the, hold on, did I forget to include s-stream? I probably did, yeah. Yeah, that needs to be fixed in the slides. Anyhow, the idea is that this is going to work even though standard toString for s would be an ill-formed expression. Because the thing is that our type s, well, that's not an arithmetic type, right? So this part here is never actually instantiated and we don't get a compiler error. So that's why if const expr is much more powerful than a regular if statement. If we remove the if const expr, then this is going to fail to compile because it's going to tell us no matching function call for call to toString, right? And that's unsurprising because, you know, standard toString, it has overloads for int and floats and whatnot, but it doesn't have overloads for s. So it's obvious that this would fail. So it is important that not only we make the decision at compile time, but we also yeah, just completely get rid of this block. This should just be entirely erased. This shouldn't even exist. And that's what if const expr does for us. And yeah, it can also save on compile times as a result. It's really just a very, very nice feature that is incredibly powerful and can be used to modernize so much code. So, is streamable of t? That's interesting. Wait, is streamable, is that actually a type trait in C++? I've never heard of that before. I don't think so. No, I don't think it is. Yeah, I can't find anything on that. Does that mean you can have any kind of syntax errors inside the block? No, that's not what it means. Like the syntax, like each of these blocks, they still need to be syntactically valid. But you can put ill-formed expressions in the block that that is then discarded. That's the point. And what I mean by ill-formed is like syntactically still valid, but you know, like a plus operator when there isn't a plus operator between it, or a call to standard toString when this call would be ill-formed, when it would be impossible, and that sort of stuff. So we can put code in here. You know, it has to be syntactically correct. But it can be doing stupid things that aren't actually possible. Yeah, if const expr 0 is not going to work as a comment. It's also worth noting that if it's going to be ill-formed, it can't be unconditionally ill-formed. Like if I do static assert false in here, it's gonna fail to compile because this false is not dependent on t, right? So the compiler does actually check whether things that are independent of the template are well-formed, right? So we don't have complete freedom, but anything that's dependent on the template, you know, it can be ill-formed, even, you know, as long as it's in the block that never gets instantiated. Yeah, I mean, you can have as many semicolons as you want, though. Yeah, that's true. If you love semicolons, you can have 2 of them, and not just 1. Okay, so let's continue onwards to perhaps a very significant, this is going to be the last part of the presentation, namely the topic of constraining templates. So far we've only ever worked with unconstrained templates. So basically templates that can accept absolutely anything and everything, and that's not always the best idea. So for instance, if you accept, you know, just any type parameter, it would be possible to have code that fails to compile. So let's go back to, well, I'm pretty sure I actually put something interesting on this slide as well. So yeah, let's say we have this wrapper type, right? And we have this issue that in principle, this can accept voids, and then it would be ill-formed. And I'll go through all of the different ways that you can sort of prevent that and deal with this problem. So this is the prettiest way, perhaps, and this is C++20, right? So with C++20, so with C++20, if you want to constrain any template, you can do so using constraints. It's really that simple. All you have to do is put a requires clause here that would verify that this type right here is indeed not void, right? So this can be any kind of Boolean expression, etc. I mean, that's useful, that's pretty, but if you're not using C++20, it gets a lot uglier. So something that's always gonna work, even C++11, is to just use a static assertion. So for instance, we could assert that static assert standard is same v, or rather not is same v, or rather not is void value. Right, so this is what it can do in C++11. It's what it can do in C++14 and 17, you know, really any standard. The question is this really all that useful? And is that error message really what we want to have? Because we're still instantiating the wrapper, it's just, you know, we're then printing an error inside of it. So perhaps, you know, an interesting metric by which to compare the different ways to constrain these things is using the error messages. So for instance, now if I wanted to have a wrapper of void, what is it gonna tell me? Well, it'll tell me static assertion failed, no void, right? So that's not entirely bad, right? That's not horrible. That's pretty good. Tells me more or less what I want to know. And if we switch to Clang, it's probably going to look quite similar. I would be very surprised if there was any major difference between what this does and what Clang tells me, right? It tells me static assert failed due to requirement. Okay. Yeah, so very similar in that regard. Now if we go back to the original, so if we use the C++20 feature, so constraints, then not standard is void v right here, right? So now this tells me constraints not satisfied for class template wrapper with t equals void. So Clang holds while GCC doesn't? I'm not sure what that means. I mean, they're both very similar. But yeah, I don't know, maybe you mean that it goes one layer deeper or that the error message is shorter, I'm not sure. But yeah. And perhaps the motivation for constraining templates in general is that you just don't want people to pass random stuff in, right? You don't want people to pass in, you know, stuff that isn't, let's say, an arithmetic type when you want to do arithmetic stuff on it, etc. So it's just a generally good idea, good practice to constrain templates in general. In C++20, that's very easy. In C++11, it's not 100% as easy. You can do it with a static assertion. Or you can use a feature of C++, which has been around for, well, basically forever, which is called a sphenae, right? So this is something that cannot be skipped, I guess, when we're talking about constraining things. And what it stands for is substitution failure is not an error. The idea is that if we try to, like, let's say put an int inside of here, and for some reason, this would be ill-formed. Like one of the other default parameters would be formed. If the signature of a function would be ill-formed, you know, if there was something incorrect about it as a result, then it won't even let us instantiate it. But that doesn't have to be an error, right? So, okay, so simple example. Let's say we have like a template type name t, and we'll use some trailing return type for this one. So ta, tb, and we want to return the result of the expression a plus b. And, well, I guess we can also make this function do something, namely return a plus b. So yeah, this is one thing. And now if we had another type that doesn't have a plus operator, this the compiler won't actually let us instantiate this. So instead of having an error that is inside of here where it'll tell us, oh, you know, no matching function call for operator plus for s, whatever, it won't ever instantiate this one. So let's see what happens. So if we wanted to have an s, I guess equals ed, we'll just, you know, add two of these s's together. So what's gonna happen is it tells us no matching function call for call to ed, and candidate template ignored, substitution failure with t equals s, invalid operands to some binary expression, right? So basically we're moving the error into the signature, and this can be a very useful feature, actually. If we use it correctly. So for instance, we can have an overload, right, that normally loses in overload resolution. Like let's say this C-style variatic function, right? Now the thing is that ellipses parameters, they always lose an overload resolution. They never get chosen unless they're the absolute last resort. So now if we had an add function right here, this should actually, wait, why exactly doesn't this work? Oh, because we yeah. Okay, this is now a hacky demonstration, unfortunately. Could have been more elegant than that. But yeah, now this now actually works, because even though s plus s, or well, an instance of s plus s would be an ill-formed expression, substitution failure occurs here, but you know, as the name says, it's not an error. So instead the compiler will just kind of say, okay, this add function, if I put an s in here and an s in here, well, that doesn't work, right? So it'll just go to the next function and it'll see if it works here. And yes, indeed, you know, you can just put anything you want into an ellipses parameter, so obviously that'll work. And yeah, so that's how that works. And so Sailor 19487 has said templates and then type name standard enable if t, not standard is void v, etc. Right? So the enable if t template, the alias template from the standard library, is a very popular way to cause substitution failure intentionally. So yeah, perhaps to demonstrate this here. So you can have another parameter in order to cause substitution failure in this in the template head, right? So it can be in the function signature, it can be in the template head, it can be in a lot of different places. So standard is void v, should definitely not be true. And yeah, that should apply to our type t. And the actual type of this is then going to be int, and we just kind of default this so that it's so that we don't have to specify it explicitly, right? So the idea of enable if t is basically that if the condition is not met, then it will produce a substitution failure for us. I'm kind of confused. Yeah, well, okay, the compilation failed. It just doesn't show up as like, yeah, it just doesn't show up as red underlined. But this fails to compile now, and it basically tells us that yeah, there was a failure when substituting void inside of this thing. And yeah, so really the idea of enable if t is basically that if the condition is met, so for instance, if we have a wrapper of int, then this works just fine. However, if the condition is not met, then it will never actually be instantiated. And that's just because enable if t just causes a substitution failure by accessing, you know, some member that doesn't exist inside of it when the condition is not met. So it's really just a way of kind of enabling sphenae based on some like Boolean condition. It's fairly straightforward. It uses the same principle that you also see here. It just kind of does it in a well, in a less direct way. It just does it through a bool that you can give it. And so you will actually see standard enable if t. You will see that so much in C++ 17 code. You will see that so much in C++ 14 code as well. If they use the alias template for it, but yeah, it's just another way of constraining things. So let's go back to the slides. So we've now kind of walked through all these different possibilities. So you can use static assertions to just kind of throw an error in the face of the user if they didn't specify the right parameters. You can use a sphenae, basically, maybe in combination with type traits such as is void v or something like that. So yeah, enable if is a C++ 11 feature actually. So it makes sphenae a lot easier to use. It's just, you know, generally a cool thing. And the member detector idiom also factors into this quite nicely. And we'll talk about this idiom in just a second. And yeah, also in C++ 20, you have by far the prettiest option with kind of concepts and constraints. So this is a constraint right here, where we just check whether this is void or not. Yeah, I mean, you can implement enable if yourself as well. Reading chat right now. That's totally possible as well. I don't think my timer I think my timer might have overflowed, actually. Okay, whatever. I might have also pressed R accidentally. I'm not sure what happened there. But yeah, the final thing I want to talk about is one really cool idiom where we kind of put all of our knowledge to the test, where everything comes together in just one big amazing idiom, which is called the member detector idiom, or I guess a way to imitate C++ 20 concepts, but before that. So the overarching goal is we have some kind of expression, and we want to basically test, like without just, you know, compiler errors in our face, whether this expression is ill-formed or not, right? So let's say we want to test whether this type S right here has a plus operator. And yeah, I'll do this from absolute scratch, because it is more fun if you do it from scratch, to be quite honest. So this is going to be a type trait, and if you followed the first part of the presentation, you probably remember you tend to use class templates for type traits, right? And it's just okay, so we start out with template type name t, because it's supposed to be a trait for, you know, some kind of type, such as S, for example. And we want a trait that tells us whether something has a plus operator, whether that would be a valid thing to do for our type, right? So we're going to call it has plus. This is the name of our trait. And so the first thing we'll need is basically some kind of fallback function, which gets called in the event that it doesn't have a plus operator. So this whole thing is going to be hijacking overload resolution and the sphenae and these kinds of features. But yeah, first we need kind of a fallback function for later. Let's say, we'll just call it test for now. And this is a function that returns a false type, right? So the false type is basically, in case you don't know this one, all that it's basically is a wrapper for a bool. So really all that it is just stores a constant, like static const x per bool value equals false. That's basically what it is. It's just a way of encoding a constant in the type system. Yeah, yeah, and while we're at it, let's just do this ourselves, I guess, without the standard library. Static const expr bool value equals true. I guess we can just do it ourselves. Who needs the standard library anyways? So now we return false type. And this is our fallback. We don't actually need inheritance for this one. We don't. Yeah, we don't go too much into object-oriented programming here. I mean, this is really template stuff. This isn't OOP. But yeah. And now, basically what we want to do is if the plus operation between two instances of our type T is valid, right? Then we want to return true instead. Right? That's the overarching goal. So our test ultimately is going to be based on this return type of our test function. So static const expr bool value equals, and we just kind of grab the return type of test of, you know, some arbitrary type. It doesn't actually matter what it is. And we just grab the value out of that. Oh yeah, and this needs to be static, by the way, in order to properly work, right? Now, anyhow, I've said that if we can do a plus operation between two instances of T, then this is supposed to be a function that returns true, right? And for this, we will use overloading. So the second function is going to be static auto test, right? And this is going to accept just an int. And the reason is we want this to win an overload resolution, because accepting an int is going to be better than accepting an ellipses parameter. And yeah, so we just kind of need anything that wins an overload resolution. It could even be empty, I guess. So now that I think about it, I mean, yeah, I guess it can be empty. I think, at least. Let's see. And this is going to return true type. Now, so far, this is not really testing anything yet. This is always going to be true. We can verify this, you know, static assert has plus for s value, and this should then be true. So yeah. Oh yeah. Oh, now it's complaining that the call is ambiguous. Yeah, so we do indeed need that int, because otherwise both ellipses and an empty function are equally good. Okay, so yeah, so far so good. However, we are still not really testing whether the plus operation between these is going to be valid. So we're still not testing for that. Then the next step is going to be to cause a substitution failure if and exactly if the plus operation between these is ill-formed. And that's pretty easy to do. We just kind of need to slap a decal type of these two s's or something like that, of these two s's added together somewhere in here. Okay, so for instance, we could do that in this argument, I suppose. So yeah, let's say decal type of s, you know, two instances of s together, and then we kind of abuse the. You know what? No, I don't want to do that. This is gonna be ugly, and I want to do it correctly right away. I want to do it right away. So one important thing is that this needs to be a templated member function. And the reason is that if we have some kind of, you know, failure, if we have some ill-formed expression somewhere in this function signature, then yeah, this whole has plus thing, that's going to just fail to compile as like on its own, right? So we need this to be a template as well. So we continue on. We, let's say, have t2 equals t, and yeah, so far so good. So far so good. We now have value right here. Which is still true. And now, you know, somewhere in here in the parameter list, in the arguments, or in the return type, we need to cause a substitution failure, right? That's how isFine works. Doesn't really matter where, just, you know, can be anywhere. And we can do that in another default parameter. So for instance, we can just make this an unnamed one that is the decal type of t2 plus, well, I mean an instance of t2 plus t2, right? So it's just an unused template parameter. And now here comes in the magic. Now this is working correctly. Has plus of our s now indeed has a false value. And why does it have that? Well, because we're testing whether, because this function right here, when we call test of 0, then normally it does prefer this in like overload resolution. But because t2 and like plus t2 come from t, and that is an s, right? And that doesn't have a plus operator. This just straight up, it just completely fails to, well, it's just ill-formed, right? So substitution fails, and this function, it basically doesn't exist for our s. There's only this one, and this one returns false type. And then we just kind of grab the return type out of this, and everything works as intended. So now we can correctly assert that indeed our s does not have a plus operator for it. But if we did, let's say, has plus of int value, then this does like pass, because an int, you know, if we instantiated two ints right here and then we added them together, this would work. It would work just fine. Well, technically, you know, this is kind of imperfect, because it's testing more than it should. It's testing more than it should, because we also test whether this type is default constructible, right? And we might have a type that is like not default constructible, but that does have a plus operator. So if you wanted to do this 100% correctly, then you would have to like decal val of t2, you know, and then another standard decal val of t2, etc. And only then does it actually work. And that's the reason why decal val exists, so that you don't kind of cause these accidental substitution failures because you wanted to default construct something, right? So now this has gotten more correct. Yeah, and Ludo Narrator has also correctly said, yes, decal val should indeed work. Well, now implement decal val. Decal val is totally easy to implement. Like it's just not evaluated. Like templates, type name t decal val, right? And there we go. That's decal val. That's how decal val works. That was pretty easy. It's also worth noting, if like t2 is an abstract class, right? Then we're in trouble, because we can't actually return an abstract class by value. So we actually need the decal val of a t2 reference. Otherwise, we're also testing whether it's like non-polymorphic and stuff. So only now is it correct. After all of these changes, only now is it correct. So yeah, and this is how you can sort of check whether whether something has a plus operator defined for it. And this is basically old school concepts. Now I'll show you the C++20 alternative, which is going to be tremendously less complicated and tremendously easier to use. So let's say if, you know, template type name t concept has plus not dump is then we just kind of need a requires expression. Oops, requires for, let's say, you know, some t value. And then we just kind of yeah, and then we just kind of do a t plus t in here. Now I'm not actually sure what happens when you don't want to test for the return type or something. I actually never had to do that. That's weird. So I'm actually kind of confused. I'll just put I'll just put something here that should work. Hold on. This should be a single one. And I think I need to include concepts for that to work. And yeah, just missing a semicolon. Yeah, I'm not actually 100% sure. Like, what, does this work? No, it needs to be a concept name. So yeah, but that is basically how we can test whether whether something has a plus operator in a way that doesn't require, you know, 10 different extremely complicated features of templates. Yeah, and I hope that this could be useful and insightful for you. This concludes our presentation. This concludes this week's Together C and C++ convention. Yeah, I know that the member detector idiom, you know, that was a bit complicated. That took a bit of time to explain, but it's really just something that I find to be really cool, and where all of these different features of templates, they just all come together, you know, Spine, overload resolution, just everything is working together so nicely here. Anyhow, that is indeed the end. I also had one prepared that also does a has plus here, and then also like tests for the return type that it's also the same as T, but yeah, not really far from what we've written on Godbolt, basically the same thing. Now, yeah, for a second Q&A session, if you still have some kind of questions regarding templates, you're free to ask away. I'll still be here for a couple of minutes if you want to ask something. Yeah, and Ziolko one, first time here. I'm now horrified. Thanks, maybe. Well, that's yeah, that's templates for you. That's templates for you. They can be horrifying, but really the thing that makes templates so amazing is that everything just works so nicely together. You know, it's just overload resolution, Spine, concepts, it's all tied together nicely in one package, and it's so powerful, and you can just do so many cool things with it. So yeah, then Halalayuafail asks why I used not. Yeah, I just use, it's a stylistic preference, you know. In principle, you could use exclamation mark as well. I use not because it's more easily visible. It's perhaps a little bit more friendly for the dyslexic or something. So yeah, it's just easier to read. It's just prettier. It's easy to miss some kind of exclamation mark, especially if you put it next to an I, like a capital I, or next to an L. You know, it's very easy to just to miss that one. Yeah, then Petu of Tzirski asks, can I use has plus to control class template argument deduction? I'm not sure. Like, well, you can use it in order to constrain stuff. I mean, you can use it as a trait to constrain things, right? So, for instance, if we, I guess, had like some kind of class template, right? Struct class. Okay, now we could constrain this using has plus now. So for instance, we could mandate requires has plus excuse me. Ah, yeah. Yeah, I apologize for the weird typing, by the way. I'm in a position where I have the microphone right in front of me. I'm not really used to it, so I'm kind of missing some keystrokes. But yeah, you can do this, right? So you can constrain stuff. I'm not sure how you would control class template argument deduction. Like, can you actually put Esfine inside of deduction guides? Yeah, I think you can. So, I mean, I don't see a reason why you couldn't. I'm pretty sure you could. So my answer is going to be probably yes. I don't see a reason why you couldn't. On a side note, we can also turn this has plus into a concept. That's probably a little bit nicer. So we can do template type name t concept. I don't know, has plus type. It needs to have a different name. Is has plus value. And now we could, for instance, use it like this. We could use our concept like this. Or we can say this is a has plus type t. Both of these accomplish the same, right? And this is just, you know, this is how it all kind of ties together. But I have to admit, yeah, like you wouldn't use the member detector idiom in C++20 because it's been totally superseded by concepts. So this is very weird to have. But yeah, you can use it to constrain stuff. You know, you can use it with standard enable if t and whatnot. So that works before C++20. And the one downside here is you need a separate one of these for basically every single expression that you test for. You can make a macro that kind of simplifies it, that prevents you from copying and pasting this. So you can make a macro that creates a member detector for you, since they always work the same. It's always the same idea with the, you know, ellipses and returning false type and whatnot. It's always the same. But it's also not particularly efficient in terms of compile times. So that's probably the reason why the C++ standard library is not constrained up until C++20. They only started constraining things when you had concepts that made this, you know, not as idiotic as this huge pile of advanced language features. Yeah, and by the way, like, this looked a lot uglier in C++98. You know, this is already using C++17 features. You should use bitend instead of the ampersand character then. If I'm using not instead of the exclamation mark. Yeah. Well, the thing is that the ampersand, like at least in a proper style guide, is going to be surrounded by spaces. So it's not easy to miss. So there's not really any necessity for it. So another question. Why not dump memos like CPP insights and reuse those to ease compilation? I'm not sure if this eases compilation. I mean, like, how would you ease compilation? The compiler still needs to create this type every single time, and I mean, yeah. It's kind of unfortunate, but I don't really see any way to speed this up by a lot. So yeah, yes, do the C++98 code for this. Okay, let's... It might be funny. It might actually not be all that different. Wait, do we have decal type in... decal type. Is that a C++? Please don't tell me that's C++11, because then I wouldn't know how to do it. Damn it. Okay. Ha. Okay, fun challenge, I guess. Do this thing in C++98. Okay, so we're like switching to godforsaken awful mode right here. Jesus Christ. Well, okay, let's get rid of all the concept stuff, right? Do this thing in C. Well, you're not gonna do this in C. Concepts isn't a thing in C++98. Yeah, we can get rid of that. Do we not have trailing return types? Okay, so let's clean up the false type and the true type. I'm pretty sure these were actually C++ 98 features. Or maybe not. But yeah, in C++ 98, I think you would more or less have to use a... Yeah, integral constant is a C++ 11 feature. So we would have to use enum value equals 0 or something like that, right? It's already getting a little funny. And then kind of the same idea here. So enum value equals 1. Right? And like everything with enums has to be evaluated compile time, so it's basically a poor man's const expr. Well, struct is just a it's basically the same as class, except that everything inside of it is public by default, right? Whereas everything inside of a class is private by default. Okay, so I don't think C++ 98 has trading return types, right? That's kind of modern, right? So we'll have to put this at the start. Okay, we can make this work. Yeah, I mean this is then gonna have to be an enum as well. Enum. Easy stuff. Do we have to? Yeah. And then yeah, we don't have a decal type yet, so that's our biggest problem. I might actually be lost here. Help me, chat. Okay, so how do we get this type? How do we get this value out of this? I think it can't be a function. I think it'll have to be some like type or something. I don't know. I think maybe with partial specialization or something like that we could do it. So yeah, maybe we could cause a substitution failure in a partial specialization. So let's do this, boys. Let's do this, boys and girls. What do we do? I mean, I guess it has to be... I mean, it's called struct test, and I guess it'll store an enum value equals 0 for the primary template. And then I guess we need to cause a substitution failure with this thing. So if we do it like this, it should be preferred, I guess. Maybe it's easier if I do stuff like this, right? What about this one? A full specialization. What's your problem? Unknown type name. Okay, I think we're still getting syntax errors from the other stuff. Okay, I think this should be fine. But yeah, let's do type name instead, I guess, and specialize at 40. Yeah, this can work. This can work. That's how we can make it preferred. I have gained hope again. You know, C++ 98 member detector. Now we just kind of need to cause some substitution failure inside of here. That should be doable. That should be doable. But I'm not sure how. How do we cause substitution failure? Maybe if we had another parameter, right, some kind of int x parameter, right, and we made this partial specialization. Okay, why doesn't this work? Well, it's not an integral constant expression, yeah, but it can be, I guess. Well, hold on. Well, we can make this unevaluated by just kind of doing a size off, right? But it still doesn't let us do it. It still doesn't let us do it. This isn't substitution failure, it just completely fails to compile. Ah, God, why do you have to do this to me? I may be at the end of my wisdom here. Oh, God. Well, yeah, so the problem is that this isn't really using as Fine right now. This is causing just a compiler error, but it's not as Fine. So I guess you can't really cause a substitution failure in the parameter, yeah, and like the deduced parameter list of partial specialization. Yeah, use the recurring, the CRTP. I don't know how the CRTP is gonna help here. This is. I mean, it would be fine if the substitution failure was, let's say, in this right here. Let's say, you know, somewhere around here. Well, this doesn't really get us closer, but if we had a default, no, even if we did this, that still wouldn't work. So does this Fine just not really work the same way in C++ 98? Does this just not work? Oh, well, yeah, well, hold on. Hold on. We haven't made it dependent yet. That's the problem. We need to make it dependent. Oh, we might be onto something here. We might be onto something. Type name. Well, n equals t. No, but we can't have some default stuff in a... in a partial specialization. But that's not a problem, actually. It's not a problem. It can just be anything. Yeah, perhaps our naming should be a bit saner, but whatever. I think we are about to crack the code right here. Well, we don't have any static asserts yet, but we can just kind of int x, int has plus. Are we about to do it? Are we about to do it? S has plus. Oh, there's no new line at the end of the file. Yeah, big problem. So I'm kind of curious why this fails to compile. All I'm getting is there's no new line at the end of the file. What? Error. This file requires compiler and library support. What? Who? What? What? Okay. Well, anyhow, we did it. We did it. Yeah, C++ 98. Member detector idiom. It doesn't look nearly as bad as I thought. We just kind of used partial specialization. That worked, I guess. Yeah, that was a fun experience. It's not even that different from how we kind of do it in more modern C++ versions. I'm thinking whether there is any kind of way to improve upon this, but I'm not seeing it. Maybe, just maybe, we could get rid of this n parameter. The problem is that we need this to be dependent on n, right? Like it can't just be t, because otherwise this will just be ill-formed independently of this partial specialization. So yeah, that's not gonna work. I guess we do need the n just so that we can like set n to be t. I don't see any better way. Yeah, okay. So are there any more questions for the Q&A? Yeah, we have answered the question whether it's possible in C++ 98. And yeah, well, Caillou asks, does it work? Yeah, it does work, evidently. You can see that int has plus is false and s has plus is 1, which is clearly correct because int does not have a plus operator. You didn't see anything. I'm confused why this is actually correct. And shouldn't be kind of the other way around. I don't get this. I honestly don't get this. I mean, what is up with this? I mean, the primary template... The primary template should be 0, right? Yeah, but I mean, like, the idea is basically that this one exists. This one exists if the plus operation between the two is valid. Right? That's when it should exist. And then the value should be 1. I mean, logically, right? So if we can do a plus between them, then the value should be 1. So I'm really confused, you know, I'm really confused why it's exactly the other way around. This makes no sense to me. What is up with this? I mean, it should work for float or something, right? Oh, wait, I'm dumb. Yeah, I'm dumb. It's like, it doesn't work. It doesn't work. Yeah. Now I see. Now I see the issue. I'm trying to implement the member detector idiom in C++ 98, which is proving to be quite annoying. This is the oldest school disgusting kinds of templates that you can work with. Yeah, archaic Ooga Booga CPP puts it well. So what is up with this? Why is this partial specialization not chosen? I mean, this is a constant expression that's like 0, right? So in principle, that should be chosen for, like, if it at all exists. But it doesn't get chosen ever. What? Non-type templates argument of type int is not an integral constant expression. This is not an integral constant expression. Are you kidding me? Are you kidding me? This is not a constant expression. What are you smoking? What, the comma operator can't be used in constant expressions? That's dumb. I don't really see why we don't get a compiler error in this case then. We did it. We did it. We did it. Oh boy. Well, I guess you can beat the system. The casino doesn't always win. Yeah, nice. Man, these are really bad diagnostics. It should have told me that the comma operator isn't a constant expression or some stuff. I mean, what is up with that? What is up with Clang? Like, would GCC have told me that I'm doing something wrong? What is up with this? Like, you know, regular x86 GCC. Yeah. Oh, look at this. A comma operator cannot appear in a constant expression. Thank you, GCC, and go to hell, Clang, I guess. Very unfortunate. Very unfortunate. This Clang has cost us a bit of time here. Yeah. Now this is... Ah, okay, it's just 4 zeros. It just... Yeah, it's still 0. Okay. Yeah, I mean, look, if Clang supports C++98 as a standard, then it should also work. You know, you can expect the correct diagnostics for it. And it clearly like messed up the partial specialization, you know, it didn't work, so I'm just confused. But anyhow, this concludes it. I think we've extended this Q&A session, or I guess this experimental session for long enough. Now here's another question though. What if you just pass size t and ignore it? Well, I'm not sure, like, what, where? Like, what are you gonna do with that? And just ignore it? Well, I mean, I guess you can... I don't see a reason why this couldn't be size t, other than the fact that we need an include for it. But I'm not sure what this changes. I mean, it can just be an int. It doesn't matter. We just need something that can be 0. Well, the point of multiplication with 0, it's pretty straightforward here, right? So the idea is that we need a partial specialization, right? So we have, you know, type name n, right? And that kind of needs to stay in both of these, right? That needs to be in the primary template, and it also needs to be in here. Because this thing right here, you know, that we want to kind of cause substitution failure, it needs to depend on n, right? So we need another parameter, basically, which can produce this substitution failure, and which we can specialize for, right? It can be int, float, well, okay, it can't be float, but it can be int, size, t, whatever. It can be really anything that's non-type. And so the idea is we just kind of have this size of expression right here, so that this is not evaluated, right? So this is unevaluated, but we still have this expression in here, and this is like still causes substitution failure if there's no plus operator between two n's. Right? However, we then multiply it with 0 so that like this gets chosen down here. So here we do test of t and 0, and so this needs to be chosen then. So that's why we multiply with 0. If it was anything else, then yeah, like we couldn't reliably choose this partial specialization, and that just kind of simplifies it. But yeah, as I've said, I think that concludes it. There are not too many questions anymore. This was a fun experience. And yeah, see you next week, where somebody else is going to present yet another interesting topic.